So to introduce our speaker for today, Nicolas Heureux, he received his PhD from the Catholic University of Louvain in the field of total synthesis and biologically active natural alkaloids. He joined DIAsource Immunoassays in 2010 as R&D and Industrialization Project Manager. And he was specifically working on the development and life cycle management of immunoassays with a strong focus on vitamin D assays. He became the vitamin D principal scientist in 2014 and continues to support the DIAsource vitamin D segment.
Thank you very much, and thank you for organizing this webinar. So in this webinar, I'm going to discuss about free 25-hydroxy vitamin D and why we think we should measure this parameter. And then, as you said, I'm going to present a tool that DIAsource is distributing together with ALPCO that allows a direct measurement of this free 25-hydroxy vitamin D. My first slide shows how 25-hydroxy vitamin D circulates in the human blood. As you probably know, vitamin D is bound to binding protein. The reason for this is that vitamin D is a very hydrophobic molecule. Hydrophobic means it's not soluble in water, so not in blood as well. It's a very carbonated molecule, not soluble in water and aqueous buffers. Because of this, it needs to be bound to binding proteins to be able to circulate in the human fluids. The first binding protein that binds vitamin D is named DBP for vitamin D binding protein. This protein has a very high affinity for 25-hydroxy vitamin D and actually binds around 88 to 90% of the total 25-OH vitamin D. Then there is another fraction, about 10 to 12%, that is bound to human serum albumin. The affinity of human serum albumin for 25-hydroxy vitamin D is about 10 times less than DBP, but the concentration of albumin is much higher, so it still captures about 10 to 12% of 25-hydroxy vitamin D. And finally, there is a very, very small fraction, about 0.04%, that circulates as the free form, and this is what we will be interested into this webinar. It's in this very, very tiny fraction that circulates without any binding protein as really the free molecule in the blood. If we take as an example a human serum sample that contains about 30 nanogram per milliliters of 25-hydroxy vitamin D, this means that about 26 nanogram per milliliters will be bound to DBP, about 4 nanogram per milliliters will be bound to albumin, and only 12 picogram per milliliter will circulate as a free form. It's a very low concentration, even lower than the classical concentration of the other known vitamin D metabolite, the 125-hydroxy vitamin D. Why do we think free 25-OH vitamin D is interesting? Well, this scheme represents the different mechanisms that explain the cellular uptake of 25-hydroxy vitamin D within the cells, which will allow its conversion into the biologically active form, the 125-dihydroxy vitamin D. So 25-OH vitamin D needs first to enter the cells before being converted into the biologically active form. There are different mechanisms that will take place in either simultaneously in the same organs, or some organs or some tissues will prefer some of the mechanisms. I'm not going to go into the details in this webinar. The first mechanism, number one, is named megalin-mediated endocytic uptake of DBP. In this mechanism, the megalin, which is at the surface of the cell, will actually bond the complex between DBP and 25-OH vitamin D. Once the complex is bound to megalin, there will be an endocytic uptake of this complex, then a separation within the cell to liberate the 25-OH vitamin D that will be then converted into the 125-dihydroxy vitamin D. In this first mechanism, the free fraction of 25-OH vitamin D does not interact, does not have any impact on this mechanism. The mechanism number two is named megalin-facilitated diffusion of free ligand. The very first step of this mechanism are the same as for mechanism number 1. I mean, the complex DBP25OH vitamin D will be captured by megalin, but then, because of this complex is located at the surface of the cell, it will allow the free ligand, the free 25OHD, to diffuse through the cell membrane. So it involves also megalin, but in this case the concentration of the free ligand is locally increased because of this complex, and the diffusion takes place directly from the free fraction of 25OHD. In mechanism number 3, we'll have a very simple passive diffusion of the free ligand. So the bound DBP25OH complex is actually in equilibrium with its free form, and the free form will simply diffuse through the cell membrane to enter the cell. So in this mechanism, clearly the concentration of free 25OHD is very important. The mechanism number 4 is similar to mechanism number 1, but it involves other receptors than the megalin. So in at least 2 mechanisms out of 4, the concentration of free 25OHD is very important in relation to its uptake within the cell and its conversion into the 125. This is similar to the situation that is already known for many years for thyroid hormones like T3 and T4, as well as for testosterone. And this whole mechanism is known in literature as the free hormone hypothesis. Because of these transport mechanisms, it might be that the free 25OH vitamin D concentration better reflects the biological activity of vitamin D than the current gold standard total 25OH vitamin D. And this is what I'm going to show you in the next slide, the few evidences that we have so far that support this hypothesis. As I said in the very first slide, the free 25OH vitamin D represents about 0.04% of the total. So can we simply calculate the free 25OHD from the total using this 0.04% ratio? Well, the answer is no, and this is no for 2 reasons. The first reason is the concentration of DBP. The concentration of DBP is not constant, and it can be influenced by a number of factors, including obesity, pregnancy, the use of oral contraceptives, hormone replacement therapy, liver disease, renal disease, proteinuria, and intensive care. I'm just showing here a range of DBP concentration data that I collected in literature, and if you look at the 3 first line, it will give you the mean concentration of DBP in, let's say, normal patients or normal subjects. You see that it's more or less between 350 and 450 milligram per liters. If we go to pregnancy samples, and not depending on the trimester or on the state of the pregnancy, the concentration of DBP is increased in all pregnancy conditions. And it's increased by at least 50 to 60% when compared to normal. In case of use of oral contraceptive, there is a slight increase when compared to normal, although this is less significant than for pregnancy. And if you look at the 2 next lines, you'll see the difference between normal weight women and obese women. And you'll see that in case of obesity, there's also a slight increase in DBP concentration. In the other direction, if we go to people having liver disease or some kidney disease, you'll see that the concentration of DBP is actually decreased. And it decreased from, as I said, around 400 to 200 or even 150 milligram per liters. So there are variations in DBP concentration, up to plus 50 and minus 50% in different clinical conditions. This will really affect the equilibrium between the bound 25OH vitamin D and the free 25OH vitamin D. In case the binding protein is present in a higher concentration, there will be less of the free form of 25-OH vitamin D. Where the DBP is present in low concentration, there will be more percentage of the free form of 25-OH vitamin D. The second reason why we cannot take 0.04% as being a unique percentage of free 25-OH in all conditions comes from the polymorphism of DBP. So actually DBP, the vitamin D binding protein, exists under different forms in human serum or human blood. These forms are named polymorphisms, and actually the predominant forms will be different for different ethnicities. Black people have as the predominant form the form which is named GC1F, while white people will have predominantly the GC1S form. Chinese and Japanese and Asian people in general will have the same predominant form as the black people, which is GC1F. There are also some additional forms coexisting, which are shown in the table below. You see these 6 different forms. And it's important to note that these 6 different forms have actually different binding affinities for 25-OH vitamin D. You can see that the form which is GC1S, so the predominant form in white, has a higher binding coefficient than the form which is the GC1F, that is predominant in black and Asian people. It's about twice the affinity. Again, if you have a binding protein having a higher affinity for 25-OH vitamin D, the percentage of the free fraction will be lower. If you have a protein that has a lower affinity for 25-OH D, the percentage of the free fraction will be higher. So this will affect the equilibrium between the bound form and the free form, as does the concentration as well. So because of these 2 reasons, the concentration of DBP that is not constant and the polymorphism of DBP leading to different forms having different affinities, you really need to measure the concentration of free 25-OH. You cannot calculate it from the concentration of total 25-OH vitamin D. This is why we think that the measurement of the free 25-OH vitamin D might be actually superior to the gold standard measurement of total 25-OH vitamin D. I'm going to present now just 3 cases from literature that have been already giving some evidence about the role of free 25-OH D. And the first literature case is from last year, 2014, from the group of Dan Bickley and Janice Schwartz in San Francisco. They have measured PTH, total and free 25-OH D in normal people, people having liver failures, and in pregnancy patients. And you can see in the scheme, in the graph that is depicted in the slides, they have compared the free 25-OH D to the level of total 25-OH D. What you can see directly from these results is that the black dots that come from the liver failure patients follow a different trend from the rest of the sample. The rest of the samples being the controls and the pregnancy samples. What do we see from here? The people having liver failures have a higher percentage of free 25-OH D versus total 25-OH D when compared to the other groups. And this is in correlation with what I showed in the previous slides about the concentration of DBP in liver failure patients. In this patient, the concentration of DBP is lower than normal, so the percentage of free 25-OH D will be higher, and this is exactly what was measured by this group. That's what they concluded in their paper. They said that the directly measured free 25-OH D was highest in patients with cirrhosis, so with liver failure, when compared to either pregnant women or to the control group, despite lower total 25-OH D. So these people actually had lower 25-OH D than pregnant and control groups, but they had higher free 25-OH D than control group and pregnant people. They also did the correlation with other vitamin D biomarkers or other bone metabolism biomarkers such as PTH and calcium. And they concluded that the relationships detected for measured free 25-OHD and PTH and calcium were at least as strong or even stronger than relationships detected for total 25-OHD and these biomarkers of the effects. The literature case number 2 comes from the group of Rolf Heureux in Scandinavian countries, was also published last year in 2014. And they did measurement of bone mineral density, BMD, but also total and free 25-OHD in a group of postmenopausal women. And they calculated correlations between the biomarkers measured and the total bone mineral density. These correlations are expressed as standardized beta coefficients, which are these numbers. The higher the number, the better the correlation. What can be seen from this study is that the correlation between the total 25-OHD and the bone mineral density is 0.080. But if you do a correlation between the free 25-OHD and the total bone mineral density, then the correlation is much better and it starts to be significant. The last line is named free 25-OHD S&P adjusted. This gives an even better correlation, and this is actually free 25-OHD that was calculated and taking into account the different polymorphisms of DBP. So they had to evaluate for each sample the predominant form of DBP and to take this into account into the calculation of free 25-OHD. Here was one of their conclusions. For bone mineral density, only the free and bioavailable measures of 25-OHD had a significant positive association, where no significant association was seen for total 25-OHD. They concluded that the results indicate that free and bioavailable 25-OHD might be a more informative measure of the vitamin D status in relation to bone mineral density. And also that you need to adjust your calculations according to DBP phenotype. That will give a better estimation of free 25-OHD. They also concluded that these findings needed confirmation in larger studies, and there are some other studies ongoing at the moment. The last literature case is from the 80s, from the group of Dan Beatley, who was one of the pioneer in the field of free 25-hydroxy vitamin D. In 1986, they published this publication where they measured the DBP concentration, albumin concentration, total and free 25-OHD concentration in liver failure and control patients. And you can see the results below. The concentration of DBP is much lower in patients with liver disease, as this is expected. It's about less than 50% if you look at the mean concentration. The concentration of albumin follows the same trend, although it's a little bit less significant. The concentration of total 25-OHD was higher in the control group. So from total 25-OHD, you would think that actually the liver disease patients are much more deficient than the control group. Now if you look at the percentage of free 25-OHD, because of the lower concentration of the binding proteins, the percentage of free 25-OHD is much higher in liver disease group than in the control group. It's about twice the percentage, or even more than 2 times. In absolute value, it gives actually similar values for the free 25-OHD for the liver disease group and the normal group. What does it mean? It means if you look at total 25-OHD, you think that the liver disease group is much more deficient than the control group. If you look at free 25-OHD, the values are actually similar, and the vitamin D status in these two groups is actually more or less the same. That's what they concluded in their paper. They said that the rise in percent free 25-OHD in the serum of subjects with liver disease compensated for the fall in total 25-OHD, such that the free 25-OHD levels remained normal in most patients, including liver disease patients. They also said that this observation may account for part of the difficulty in correlating 25-OHD levels to the presence of osteomalacia in subjects with liver disease. So from the data of total 25-OHD, you would expect more osteomalacia in liver disease patients because you think people are more deficient. But actually, if you look at the free 25-OHD, the concentration is the same, and that would explain why there is no more osteomalacia in liver failure patient than in the control group in this study. So as a conclusion of this first part, there is increasing evidence that the measurement of free 25-OHD is superior to the measurement of the gold standard total 25-OHD in multiple clinical conditions. I've just presented 3 cases from literature, but there are more than 35 references available so far, and these can be found in our DIAsource technical review. And just to let you know that there will be more evidence presented this year at the coming vitamin D workshop that's going to take place end of the month in Delft, the Netherlands in Europe, but also at ASBMR, which is going to take place in October 15 in Seattle, US. So we know that we have to measure free 25-OHD. How do we measure it? There are different techniques. The first technique was developed in the 80s by the group of Dan Bickley and was called Centrifugal ultrafiltration. I'm not going to go into the details of this technique. You can find the details in the reference of Dan Bickley. But please remind that it's a very, very time and sample consuming method. It takes days, it takes milliliters of samples. It's clearly not suitable for either routine analysis of free 25-OHD or even for analysis of large cohorts of sample. It's a very laborious method, and it requires specific equipment because you will use tritium-based molecules as well as carbon-14-based molecules, so radioactive material. So this method was a very good method, but it's clearly very, very difficult to reproduce and very, very difficult to use in a clinical laboratory. So from this method, people have been mostly using calculations. You can calculate the concentration of free 25-hydroxy vitamin D from the concentration of total 25-OHD and from the concentrations and binding coefficients of albumin and vitamin D binding protein, DBP. The drawbacks of these calculations are first that it requires 3 different measurements, total 25-OHD, albumin, and DBP. The fact that DBP is an expensive analysis and is not available on the usual platforms you would find in laboratories. Moreover, there is a strong controversy on the quality of commercial DBP assays, and there are more and more evidences coming out of research groups showing that the DBP assays are not all equal and are providing different results from assay to assay. And ideally, these calculations should also include a 4th measurement, which is the genotyping of DBP, because you need to determine for each sample what is the predominant form of DBP so that you can use the correct binding coefficient and really get accurate calculations. Because of all these drawbacks, there are several research groups who have recently called for a direct measurement of free 25-OH vitamin D instead of using inaccurate calculation methods. And an ELISA assay has been developed from this time to be able to do a direct measurement of free 25-OHD. Here are some of the assay features. It's a unique assay and it's patented. There's only one assay currently available for researchers. It measures only the free fraction of 25-OHD. It uses a very low sample volume of 10 microliters, which is very useful if you have large and precious cohorts of samples. It features a very high sensitivity, which is required because we have very low concentration of picograms per milliliters. It has a very good intra and inter-run reproducibility, as we will see in the next slides. The measuring range is broad enough so that there is no need for dilution of samples. It's calibrated against the rate dialysis technique, which is somehow a commonly accepted reference method for the measurement of free molecules, free hormones. There are 2 kit controls included in the assay so that every run can be validated by the end user. And it's at the moment a research use only kit, so only for researchers at the moment. The assay was developed by our partner companies in the Netherlands, Future Diagnostics, using DIAsource vitamin D antibodies, and is exclusively distributed by DIAsource and selected partners such as Alpco. Here you will find some more information about the assay. It's a classical ELISA microtiter plate assay featuring 96 tests. It uses serum as the sample, but plasma can also be used. The volume is very low, as I just said. There's two controls in the kit, one low and one high concentration. The range is broad from 0.2 to 35 picogram per milliliters. The limit of blank and limit of detection are in the range of 2 picogram per milliliters, and I will come back a little bit later to this sensitivity data. The precision profile, the reproducibility profile is good, from 10 to 5.5% of CV. The specificity profile is this one, and the cross-reactivity to the D2 form of vitamin D was measured and was about 77%. So it can also measure the free 25-OHD2, although not with 100% recovery. Total incubation time is rather short, 2 hours 30 minutes, which is classical incubation time for an ELISA, and it features 4 different incubation steps, as we will see later in the detailed protocol of the assay. This is the principle of the assay shown on the right of the slide. In the first step, you'll see that on the right of the slide we have represented the wall of the microtiter plate wells with the antibody coated on the microplate. On the left part of the scheme, you'll find the DBP-bound 25-OH vitamin D, which is in equilibrium with the free form. If you don't add anything in this situation, the affinity of the antibody is not sufficient to capture the free fraction. The free fraction will mostly remain within this equilibrium with the bound form. So we needed to add a very small quantity of release reagent that will actually push a little bit this equilibrium towards the free form, so that the free form of 25-OHD can be captured by the antibody. And the type of release reagent and the concentration and incubation times were optimized so that the antibody can capture the exact amount of the free 25-OHD. After a wash step, there will be a competition between the 25-OHD that was captured in the first step and the labeled 25-OH vitamin D labeled with biotin. The rest of the ELISA is a classical ELISA. Streptavidin HRP will come in the next steps, then TMB as a substrate and the stop solution. And we will see the protocol in the next slides. This is the protocol of the assay. First step is an addition of 90 microliters of sample diluent with 10 microliters of either calibrator, control, or sample. This sample diluent contains the very small concentration of the release reagent that is needed to allow the antibody to capture the free 25-OHD. There's a first incubation step at 37 degrees with shaking that will last for 90 minutes. Then there is a wash, and 100 microliters of biotinylated 25-OH vitamin D are added. There's a second incubation steps during 30 minutes at 37 degrees with shaking. Then there is a wash step again, and the streptavidin HRP reagent will be added to the wells. There's a third incubation steps for 20 minutes at 37 degrees with shaking. Then again a wash, adding of the substrate, TMB. A fourth incubation steps that this time takes place at room temperature without shaking in dark and will last for 15 minutes. After the addition of stop, the microplate is read at 450 nanometers and the results are calculated from the standard curve as a classical ELISA. The incubation at 37 degrees with shaking can be performed with different equipments. If people don't have an equipment available, we can provide this DIAsource ELISA shaker incubator, but you can also use your incubator if it's suitable for shaking and heating at the same time, or you can even use a classical ELISA shaker which you would place in a calibrated oven at 37 degrees. So all different setups are accepted. On this slide, I'm just going to show how we calculated the sensitivity. So limit of blank is the smallest concentration that can be differentiated from the blank of the assay. It is calculated using 60 replicates of a sample that does not contain any 25OH vitamin D. And it was calculated to be 1.9 picogram per milliliter. The LOD, the limit of detection, is the lowest concentration that can be actually detected by the assay. It is calculated by measuring 5 samples with low 25OHD in 12 different runs. It was calculated in this assay to be around 3 or 2.8 picogram per milliliter. The precision profile was calculated according to CLSI guideline with these references EP05/A2. We used 3 samples across the concentration range. The first sample was around 6 picogram per milliliter, second sample was around 11, and the third sample was around 25 picogram per milliliter. The measurement took place over 20 days, performing 2 runs a day in duplicate. And for statistical reason, the order of the samples was different in the 2 runs every day. So from all this data, the CV were calculated for each concentration. You can see that for sample 1 at around 6 picogram per milliliter, the CV is the highest. It's about 10.2%, which is still very acceptable for an ELISA test. Sample number 2, with a mean concentration of 11 picogram per milliliter, featured a CV of 7.6%. And sample number 3, at the highest concentration, 25 picogram per milliliter, featured a CV of 5.5%. This is the end of the presentation. I just want to give you these few take-home messages. The first message is that free 25OH vitamin D represents 0.04% of total 25OH vitamin D. Second message, the concentration of free 25OH vitamin D is directly linked to the biologically active 125OH2 vitamin D through transport mechanisms that involve the concentration of free 25OH vitamin D. Because the DBP concentration is not constant, and because DBP exists under different genetic forms, the percentage of free 25OH vitamin D is not constant amongst clinical populations and should be measured. It cannot be just calculated from the total 25OH vitamin D. There is more and more evidence in literature that the measurement of free 25OH vitamin D is superior to the gold standard measurement of total 25OH vitamin D, especially in conditions where DBP concentrations and DBP forms are different from normal. Clearly, the direct measurement is preferred over inaccurate and laborious calculations for different reasons. One of the reasons is that it needs 3 or 4 different measurements, and also that the quality of the DBP assays is not equal amongst all assays on the market. And finally, please be aware that DIAsource and ALPCO distribute the first and only direct measurement method, which is a classical ELISA assay that will allow you to directly measure free 25OH vitamin D in your samples. The next slide features our contact data at DIAsource if you need to contact us for any reason. And on the next slide you'll find the contact data of Bethany from ALPCO. Thank you very much, and I think now there will be a few questions.
Thank you, Nicolas. Yes, we do have a couple of questions for you. So the first question is, does the direct measurement correlate with calculated free vitamin D using the binding protein affinity constants?
Okay, that's a very good question, and that's one of the first things we've been doing when we've been developing and launching the assay, because most of the literature, most of the recent literature was using calculations, so we needed to verify how the direct measurement was behaving against calculations. This was done by the group of Dan Bickley, and the reference is in the technical review that I presented in a few slides before. So they did actually correlation between the directly measured free 25-OHD and the calculated free 25-OHD. Calculations were made using DBP and total 25-OHD and albumin concentrations. Of course, the correlation was not perfect because, as I said, the calculations are inaccurate because of different reasons. And what they did found was that direct measurement was superior to calculations, especially with relation to other vitamin D or bone metabolism biomarkers such as PTH and calcium. The direct measurement was superior to the calculations. So there is some correlation between the two, but they've shown that the direct measurement is preferred over the calculations.
Thank you. The next question is, what is better, measuring free 25-hydroxyvitamin D or measuring 1,25-dihydroxyvitamin D?
That's a very good question. I think we have two different cases. 1,25-hydroxyvitamin D is currently used in specific clinical conditions. It's especially a very good parameter to be measured in patients fit during dialysis, so people having kidney disease, chronic kidney disease, and having to do dialysis. In this case, it's very important to measure 1,25-dihydroxyvitamin D. There are some other specific clinical conditions in which it is important to measure this parameter. But if you want to evaluate the vitamin D status of an individual, whatever its clinical conditions or whatever its disease, the current gold standard measurement is total 25-hydroxyvitamin D. And we believe that the free 25-OHD measurement will replace, or at least in some clinical conditions, the measurement of total 25-hydroxyvitamin D. The 1,25-dihydroxyvitamin D will remain an interesting and an important measurement in some specific conditions, such as kidney disease and some others. But the free 25-OHD is really an alternative to the measurement of total 25-OHD and not an alternative to the measurement of the 1,25-dihydroxyvitamin D.
Thank you. So the next question is, if a releasing reagent is employed, how is this assay different from a total 25-hydroxyvitamin D assay?
Yeah, that's another very good question. So basically, a total 25-hydroxyvitamin D assay works by two main types of methods. It either destroys the binding proteins, for example, using acidic or alkaline conditions, or it will completely release the total amount of 25-hydroxyvitamin D from the binding proteins, using also a release reagent. But in the case of a total vitamin D assay, we'll use very high concentration of release reagent so that the completion, the total quantity of 25-hydroxyvitamin D is released from the binding proteins. In the case of this assay, so the free 25-OHD assay, the concentration and the nature of the release reagent has been optimized, and the concentration is very, very low if compared to a total 25-OHD assay, so that it will only slightly disturb the equilibrium between the bound form and the free form. It will not release the total amount of 25-OHD, it will just slightly disturb the equilibrium so that the antibody can capture the free 25-OHD. So it's really different, especially from the concentration point of view. We are really talking about different orders of magnitude. It's completely different from a total 25-OHD assay.
Thank you. And the last question I can answer. Someone had asked if this test is available in the United States. Yes, ALPCO does have these tests here in-house, and feel free to reach out to myself or anybody here at ALPCO if you are interested in evaluating this kit or if you have any other questions. So that concludes the webinar. Thank you for your time, Nicolas, and thank you everyone for participating.